Okay, hello everyone. Let us do some computer science today. So, we don't have a lot in terms of announcements for today. I guess all we really have are that Project 2 will be coming out probably Friday sometime. And probably midterm 2 will also be coming out. Probably Friday or Saturday. And so midterm 2 will have an MCQ part, and it'll have a coding part, and that's basically it. So it's going to be like 5 questions here, and maybe something like 13 questions here. Same thing as, does Project 2 need classes? Project 2 will use classes, yes. So Project 2 will require classes. Okay. So I think currently that's the only set of announcements that I have right now. So I guess what we're going to do is move on to, Project 2 is going to be 2 weeks. The midterm will just be 1 week. And, I might... No, I mean, we'll see. We'll see what I can do for you in terms of Project 2 time, but yeah. Okay, so I think that's basically it for announcements. So let's begin. So today we're going to be talking about sorting. So what is sorting? Basically, sorting is taking a list of elements and putting them in order. Generally, we mean ascending order, but if you want to do descending, it's fine. It's just we normally mean ascending order. So that means that if you have a list like, let's see, 7, 3, 6, 5, 1, 2, then to sort the list, you would just put it in 1, 2, 3, and I guess I didn't put 4 in here, so 5, 6, 7. Right? So this is the sort of that. Alright, so basically it just means take a list and make a new list where everything's in order. Alright, so why do we talk about sorting in computer science? And the answer is it's because it's basically the first class of kind of standardized algorithms that you get into. When you talk about data structures, when you talk about algorithms, when you talk about other things, there's string matching algorithms, there's graph algorithms, there's tree algorithms, all that kind of stuff. But when we talk about, basic computer science, I think the first algorithms that are usually called quote-unquote algorithms that you usually run into are the sorting algorithms, and they're kind of the most useful in many cases because, for obvious reasons, sometimes you want to put things in order, and that would be helpful to you. Okay, so sorting is a process that has many different solutions. Okay, so you might hear things like bubble sort, selection sort, insertion sort, merge sort, quick sort, heap sort, which we won't cover this one, bucket sort. Probably won't talk about this one, etc. So there's even more sorts than that. There's like a bucket sort is kind of, sometimes it's also called a radix sort. So kind of the same thing as bucket, in a sense, kind of not. Again, it depends. Yeah, all sorts of sorts. And so generally, so the reason why, believe it or not, the reason why we're not going to talk about heap sort is because heap sort requires basically 341, to talk about because you need to talk about heaps. But the rest of these are actually completely doable by us. Bubble sort, selection, insertion, merge, and quick. And they're usually divided into two categories. What I'll call the quadratic sort, which is bubble, selection, insertion. And then what I'll call like the n log n sorts. You can call them logarithmic, but technically it's not quite logarithmic, it's n log n, not just log n. But now, of course, you don't even know what I mean by n log n, but the point is that generally the way to think about it is that, and so by quadratic sorts I mean n squared sorts. And so I usually refer to them this way, and the reason why is because it explains kind of how these things function. And so let's go over, let's start with bubble sort, right? So bubble sort is a kind of silly sort. But it's good to start out on, right? So how does it work? So let me show you how it works. Let's make up a new list. Let's say 4, 8, 2, 1, 5, 7, 9, 3 again, maybe, or did I even? Okay. So here's a list. So what bubble sort does is it goes through the list like this, and what it's going to do is if the two things are in order, each pair, it's not going to swap, and if they're out of order, then it will swap. So the first thing it's going to do is it's going to swap 2 and 8. So basically, go through the list, swapping each pair if not in order. Okay, so 2 and 8 swap, and then 8 and 1 have to swap. And then 5 and 8 swap, and then 7 and 8 swap. But then 8 and 9 don't swap, because 8 is smaller than 9, so that's good. But then 3 and 9 swap, and finally 5 and 9 swap. So here's the one thing we know after the first step of bubble sort. Right? The thing that we know after the first step of bubble sort is that the biggest element, right, has been being swapped to the back, right? So that's what we know. We know the biggest element's been swapped to the back. But then you say, well, this hasn't sorted anything. Okay, so this hasn't sorted anything. Yes, I guess, yes. Actually, uppercase A is 65 and lowercase a is 97, so I guess if you were sorting letters, then yes, capital A would go first. But we're just talking about numbers here, okay? So let's do it again. So now we're going to scan through the list, right? 4 and 2 swap, 1 and 4 swap, 4 and 5 don't swap, 5 and 7 don't swap, 8 and 3 swap, 3, 8, 5 and 8 swap. Cool. So now what we see is 2 elements are in the right position. Okay? And so now let's do it again. 1 and 2 swap. 2 and 4 don't swap. 4 and 5 don't swap. 5 and 7 don't swap. 3 and 5 swap. 3 and 7 swap. I got ahead of myself just a little bit. 3 and 7 swap. But then 5 and 7 swap. 7 and 8 don't swap. 8 and 9 don't swap. So now we have 3 in the right position. Cool. Let's do this again. So 1 and 2 don't swap. 4 and 5 don't swap. But 3 and 5 swap. Careful, careful. This is 3. And then 5 and 5 don't swap. Or I guess it doesn't matter if they swap, but let's pretend that they don't because 5 and 5 are in the same order. 5 and 7 don't swap. 8 and 9 don't swap. And we are done. Almost there. Right? I think this is going to be our last iteration. So 1 and 2 swap. 1 and 2 don't swap. 3 and 4 swap. 4 and 5 don't swap. 5 and 5 don't swap. don't swap, don't swap. And now, basically, okay, let's go again, right? So this is how the program's actually going to work, because this one did a swap. So we did a swap here, so we can't quite stop. But here's how we do stop. What we're going to do is say, do we swap? No, 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 no. So once we get through the list and once we see no swaps, then we're done. Okay? So that's how we know that the bubble sort is finished. So bubble sort is finished when you go through the list and you don't have to swap. And you think about why that's true, right? Why does that work? And the answer is, well, because if you did have to swap, something was out of order. But if you had exactly 0 swaps, then everything's in order. So we're good, right? We don't need to do anything at that point, right? Everything's in order, so we're happy. Let me just save this. Okay. Because I'm probably going to post this as some lecture notes after class. I just want to make sure that it doesn't... okay. Didn't want to save. Okay. Sorry, I'm just dumb. Yeah. Okay, there we go. Alright, so if you had exactly 0 swaps, then everything is in order and we don't have to do it. Alright. So, now, as I always say, let's code it. I don't know if I always say that. In fact, I probably never say that, but who cares? Let's code it anyway. So let's look. Here it is. Pull up our PyCharm. Let's make a sorting thingy file. Right? So bubble sort is going to take a list, and what we're going to do, let's actually, you know what, let's write a swap function. And so this will be a little helper function. So what we're going to do is we're going to say temp is equal to the list at I. Then we'll say the list at I is equal to the list at j, and the list at j is equal to temp. So this is a swap, right? Because what you do, and so if you think about it, there's no way to, oh, that should be j. So there's no way to swap something, swap 2 elements without a temporary variable. And the reason why is because if you try to put the thing from j into I, then you're going to overwrite I, so you have to save it. Or if you're going to put the thing from I into j, then you'll overwrite j, and then you have to save that. So there's no way to do a swap that's without a temporary variable like this. So this is kind of what I always do with my swaps. Is I always kind of do the diagonal method. I look at it and say, okay, the list I, the list I, the list j, the list j, and then I pretend that you can kind of overlap and say temp, temp, right? So that's how I look at it. I just kind of go check diagonally to make sure that all of them are satisfied, and if that's the case, then we're happy. Okay, so let's make a Boolean variable called swapped equals false. Well, actually, let's set it to true, just for this time. And then we'll say while swapped. Okay. And then here we'll set swapped equal to false. And then what we'll do, and so this is what's going to actually terminate our loop, right? Because once we haven't swapped for a full time, and I'll show you what I mean by that. Once we've gone through the list once and haven't swapped, then swapped will stay as false, and then it'll exit. And we can actually return the list, which will be sorted. Technically, the list is mutable, so you don't have to return it. It will just sort the list in place, but whatever. Okay, so here, how do we do the bubble sort? And the answer is for I in range when the list, but here I'm going to have to do something a little bit tricky. -1, right? And so you might ask, why did you do the -1? And the answer is, well, what am I actually going to do here? Stop making at sign. Why did I do the -1? I did the -1 because if you think, what I'm actually going to be doing is I'm going to be doing a swap on the list x and, or I'm sorry, this is not really why I'm doing it. Why I'm actually doing it is because when I compare pairs of elements, right, I'm going to be looking at the ith element, and I'm going to be looking at the I plus 1th, or I plus 1st, or whatever you want to call it, element, right? And the thing is that if I add 1 to I, when we're at the length of the list -1, then we'll have an overflow, right? We'll go past, or I guess really I should say an index error. We'll go past the length of the list, and it won't be good. So that's why I'm subtracting 1, because basically whenever I get to the element right before the end, that's when I stop. I don't stop at the end, because otherwise then it'll try to compare itself with an element that's not even in the list, right? It'll try to go one too far. So basically, you need it to prevent going too far. Okay, so now let's say, and now how do we detect if something's in order? So if something's in order, then the list at I is going to be less than the list at I plus 1, right? So this would mean that it's in order. But we don't want that. We want it to be out of order. So what if it's out of order? So if it's out of order, I'll flip the inequality, then we'll swap the list at I and I plus 1, and then we'll set swapped equal to true. And the reason why we're setting swapped equal to true, remember, is because once we scan through this for loop, if we don't find anything that needs to be swapped, we'll never change. So swap gets set back to false every time. So it's like someone turns off the light switch, and then if this part of the code detects something out of order, it'll do the swap, and then it'll ask, is it necessary? If you've done one swap, it could be necessary that you'll have to do another swap on the next iteration. So that's why it said swapped equal to true. And then we'll go through again and again and again until eventually this for loop will run through, and this will never happen, right? It'll never be the case that the list I will be bigger than the list I plus 1, because we'll have swapped everything into the correct positions. So eventually this thing will stop setting it to true, and this thing will continue setting it to false, and then the while loop will end. So that's basically how to code up bubble sort. So let's test out bubble sort a little bit. So let's write a bubble sort test. And let's say the number of tests, the size of list, and that's it. So remember, the reason why I don't return anything for swap is because basically the point is that the list is a list, and so it's mutable. And so what I mean by that is that what happens is it the slowest sort? I mean, I think there are slower sorts, but they're kind of memes. So it's a pretty slow sort. So the thing here is that the reason why you don't have to return from the swap function is because this list here is actually the same as this list here. When you pass it in, it's not making a copy, it's a reference. And what I mean by that is that whenever this list gets passed in and we make this modification, it's making it in this list as well. So it's not just a copy. If this were just a copy, then yes, we would have to return it. But here is actually making the change first index, second index. Okay. So let's see what this does. So what are we going to do? Probably do some forbidden stuff. That's okay. Import time, import random. Yeah, I mean, I would say that, so I'm going to say that no one actually uses bubble sort. The only reason why we teach it is because it's kind of like an easy introduction to sorting, right? That's why we actually teach it. We don't teach it because it's like industry standard and that it gets used. It's something that generally doesn't get used very often, but yeah. Okay, so the bubble sort test, let's say for I in range, or let's say for test in range 1 to tests plus 1, so that it's all into, so that it starts at 1, and then we'll make a new list. So list to sort is going to be equal to say random.randint, say 0 to 100 for blank and range. And this is forbidden, by the way. I'll go over how to use these things towards the end of the semester, but basically I'm just trying to get some code up and running. Okay, now what? So now we want to run bubble sort on the list of, list to sort. And, okay, so that's what we really want to do. Copy of list equals list of list to sort. And so, why am I making a copy? So what we're going to do is we're going to test to make sure that this thing is actually sorting correctly. So the way to test that it's actually sorting correctly is to use the inbuilt Python method. So we can say copy of list.sort. Now, excuse me. I'm going to tell you exactly what method this .sort uses. It's not bubble sort, but we'll get to that. Okay. So now what we'll do is we'll test to see if sorted list, if list to sort is equal to copy of list, then we'll print out the list was sorted, and else we'll print out the list was not sorted, and then we'll print out and we'll just print this out to make sure that so this is for debugging. Hopefully we never actually see this, but if I make a mistake, then we will see this. Okay, so let's see what happens. Let's run some bubble sort tests, and let's run it for maybe 10 tests, let's say, and for the size of the list, let's make it 100. Okay, so let's just do that, and okay, let's run it and see what happens. I guess I should put an if name equals main here. Sure, let's do this. Okay, my typing is really I'm not doing very well today, but doesn't matter, doesn't matter. Okay, let's hit it. No, not that, this. Okay, so it says the list was sorted. Okay, so none of that really helps us understand what's going on here. So let's print out the current list, and so we'll see what happens here. Let's only run the test once. Okay. So here is what's actually going on. What we're seeing here is that ooh, this is a lot of stuff. Let's make the list of size 10. Here we go. This is better. So you see that 67 is the biggest number, so this is the original list. And then this is what happens after one set of swaps. And then we have another thing that happens after 2 sets of swaps, 3 sets of swaps, 4 sets of swaps, 5, 6, 7, and 8. And then we notice that the good news is that we didn't have to do 2 more because these 2 just magically ended up in the right position. It's possible that this could have been even more screwed up, and this could have still been 6-2 if the list were slightly different, right? And if that were the case, then the point is that it's possible that at the last step you would have had to do one more of these swaps. Okay, so that's basically how you have to do it, and that's how it works. So now let me pull up the actual visualization, and let us look at the visualization for bubble sort. So let's randomize an array, and then let's run a bubble sort on it. So this is how bubble sort works. It's comparing and swapping like this. And you notice that at every stage, what happens is it'll pick up whatever the biggest element is and kind of push it towards the back. But it's doing a lot of swaps, right? Yeah, you guys can play with this too. So as you see, what it's doing is it's picking up, it's swapping until it basically, quote-unquote, finds the biggest element. It doesn't know that it's found the biggest element, but what it does is it kind of it swaps until it finds the biggest element, and then it pushes, yes. The point, yes, we are only ever talking about 1D lists. It's hard to know what you mean by sorting a 2D list, right? Because sorting a 2D list can be, you have to define what it means to be in order, right? It's like, how do you sort? I mean, it's literally the same question, as, like, for instance, how do you sort a like a real numbers on the real plane? So, for instance, like, is the pair 1, 0 bigger than 0, 1, or is 2, 0 bigger than 3, 3, or whatever? And the answer is, you have to define some extra kind of thing on that, because there's no sense in which a 2D thing can be sorted that easily. Okay, so that's all I really want to say about bubble sort. Bubble sort is bubble sort. So now let's talk about selection sort. So selection sort is kind of, I think it's the easiest sort to think about. And the reason why I think it's the easiest sort to think about is that selection sort, to me at least, I tend to, at least the way I teach it, I tend to call it the find max sort. Okay, so selection sort, actually I'll put this in the other document. Where is it? So selection sort, on the other hand, is basically a find max sort. And so basically here's the algorithm that does selection sort, and then we'll look at the visualization, and then we'll code it. So what does selection sort do? What it does is it says, for I in range len my list, right? Or maybe I should make this a little bit more pseudocodey. For each index in the list, right? Or what are we going to do? We're going to find the max, and then we will put it at the right position. And we know what the right position is, and let me explain how we know the right position. So for each index in the list, starting at the end, basically, right? So we're going to find the max of the whole list, and we'll put it at the end. And then we'll find the max of everything except for the last element, and we'll put it at the second to the last. Or you could, there's another way to do it where you can have this as a find min sort. We'll talk about that in just a second. So, actually, let's just do it the find min way. So, basically what we're going to do is we're going to find the minimum of the list from the index to the end, and then we're going to put it at the right position. So let me show you what this means. Okay. So for instance here, if I have a list like 2, 7, 3, 1, 9, 5. So here's what it does, right? The first thing, yeah, it's going to look very similar to the bubble sort, but it's not. But you're right that it's not exactly the same as the bubble sort. So because it doesn't do swapping along the way, what this does is it finds the min. The min here is 1, right? So the next generation is going to be, it's just going to swap the 1 and the 2 like this, and then it's going to find the min, but it's only going to find the min from here to the end. The min here is 2. So then it's going to do this again, so it's going to swap 2 and 7. And then it's going to find the minimum again, but here it's only going to do the minimum from 3 to the end, where it's going to find 3. 3's in the right position, so it doesn't have to swap. So now it's going to look at this, from this to the end. It's going to find 5. So it's going to swap 7 and 5. 5, 7. And then here it's going to find 9. Oh, wait, no, I'm sorry, 7 it's going to find because it's looking at this. And so then what it's going to do is do this. And then technically, you can say find the minimum 9, swap 9 into the 9's position. But really the answer is you're done, right? You're already done. So this is a very similar sort to the bubble sort. But in this case, what we're going to do is every step we're going to find the minimum, and then we're going to put the minimum in the right position. What this does, the slight improvement over bubble sort, so this is a slight improvement in general over bubble sort. And the reason why it's a slight improvement in general is because it will generally run fewer swaps. A lot fewer swaps. So basically, we're reducing the number of things that the thing is doing. So, okay. So it's a better sort, so it should run a little bit faster. But of course, we'll run some experiments and actually test this in just a bit. So let's actually watch what selection sort does to this list. Let's see, is it going to be max or min? Ooh, terrible, terrible. Sometimes this thing glitches out pretty badly, and now it's glitching. So this is incomprehensible gibberish. Okay, let's load it up again. Hit it with selection sort. So you see what it's doing here, right? It's looking for the maximum, right? It's looking for the minimum. And so here it's going to find 3. And once it finds, so it thinks it has it at 10, and then it sees 8, and then it sees 3, and then 3 is actually going to be the smallest. And then it's going to scan through again. It found 7. It's going to find this 7 now. Then it's going to find 8, I guess. Then 10. I think there's another 10 right here, so it's going to find this one. And then 12. Right? So this is how this sorting algorithm works. It's going to find the minimum, and then it's going to put it in the right place. And we know what the right place is because we have an outer for loop that's tracking what index we're on. So this is the outer for loop is indexing every time it swaps like this. Right? Every time it goes through a single scan, that's one index of the outer for loop. The inner for loop is doing the scanning. Right? So that's the whole point. So here we go. And you see it does take a while to do on a list like this. It's still not the most efficient sort to use, but it is just a different sort to have in your head. So you think about how sorts work and stuff like that. So okay, and you see that it gets better as it goes on because as the size of the list gets smaller, it only has to scan through smaller numbers of elements. So, okay, so let's write selection sort. Right? Selection sort. Okay. Oh, I mean, I prefer selection to bubble sort, but we'll get introduced to some better sorts in just a little bit. So when you see insertion is going to be better than both selection and bubble. And then when we do the logarithmic sorts, they're going to blow them out of the water. So, but yeah, I mean, yeah. Selection sort's actually pretty easy to write. You just go for I in range len list, right? That's the outer loop, done. And then you say min index is equal to I. And then what you do is you say for I, or for j in range, let's say, we'll start at I, and we'll go, well, actually, we'll start at I plus 1, and we'll go to the length of the list, like this. So we see that we're only scanning the part that we don't already know, right? Because everything before I has already been put into the right position. And so then what we do is we say, if the list at the min index is bigger than the list at j, then the list at min index is equal to j. There we go. So you see what this is doing, right? It's scanning through and it's saying, if the list at what we think is the minimum index is actually not the minimum because there's something smaller than it sitting at the list of j, then we set the min indexes to j and then keep scanning. And so by the end, we should have found the minimum. This will, well, it won't find exactly the minimum, it will find the minimum index. What I mean by that is it's the index where the minimum is. And that's more important than finding the actual minimum, because the next thing we're going to do is we're going to say if I is not equal to min index, right, swap like this, and then return the list. And that's it. That's it for selection sort. So selection sort is pretty simple. Definitely not. I think it's probably the easiest sort to understand. I think it's a pretty good sort in that sense. So it's pretty easy to understand, and that's good. Okay, so let's yeah, actually let's print out the list each time to see what happens. Let's do a sort test. And then let's say yeah, so basically this one is just finding the minimum index, and then if the minimum index is not equal to I already, just run the swap function on it. And so at this point what you know is so bubble sort is going to run a ton of swaps. It could run as many as n squared over 2 swaps. Are we doing something so there's something called binary search. If you want to invent something called binary sort, what you actually mean is probably merge sort, which we will cover. Yes. So let's run the sort test. Let's run it on, say, maybe 2 lists of size 10, selection sort. And so what we're doing here is we're just checking out, this is just testing to make sure that the selection sort algorithm actually works, because it's always possible that I've written something with bugs in it. So let's run it. So here, let's look at what happened here. So first, we have an unsorted list. The minimum here is 2, so it puts it here. And then the next minimum, I guess, is 17. I guess the next minimum is actually 41, which is pretty high. And then 49. Yep, actually 49 doesn't have to move. 64 doesn't have to move. Oh wait, yes it does. Yes it does. What's going on? So 2 got shifted. I agree. 17, 41, 49 got shifted. Then it found the other 49, found 54, found 64, found 82, found 92, and 100 is at the end because it's the max. Let's check the other one. So here we scan through the list. 2 is the minimum again. 2. Scan through the list. I guess 10 is the minimum. Put it there. And remember, we're swapping it, so it's the greater elements are always getting pushed further in the list. They're not actually being put in their correct positions. They're just kind of being randomly put in. Okay, so you want to do it with max instead? Let's do it. So I think what I would do in this case is I would probably, if we're doing the maximum, then what we want to do is we want to find the maximum from, we can't do it with the middle. Finding medians is actually more difficult than you would think. So we can't do that. And so here, what we'll do is we will just say the max index is this max index. So for max index, you actually want to flip the inequality. Max index, max index, max index, like this. And then we will set the max index to the length of the list minus 1 minus I. I think this works. I could be wrong. Let's test this one out and see if I've done everything right. So what changes did I make here? So here I'm actually setting the max index to be the element. So the first time when you run it with 0, it's going to be the last element in the list. That is going to be the element before that, and the element before that, and the element before that. And then here we're going to scan up to that point, and we are going to scan all the elements in the beginning of the list. And then if it's not the max index, then we'll swap there. And I think actually I need to change this to that. This is why I did the minimum one, because otherwise you have to do a little bit of index calculations. Yeah, so think about the length of the list minus 1, right, is the last element. And so then the length of the list minus 1 minus I is I elements from the end. That's the way to think about it. So we're starting at I elements from the end. Okay? So if you do something like the length of the list minus 1, but you want 2 elements before that, then you would do the length of the list minus 1 minus 2, which is overall the length of the list minus 3. And so that'll get you 2 before the end. Yep. And so I think this works. Let's run the test on it. Let's run, say, 10 tests on lists of size 1,000 and see what happens. The list was not sorted. Oh. Huh. Looks pretty sorted to me. Oh, no problem there. I don't know if that's having anything to do with it. Oh, it caused more problems. I mean, I guess this should really... caused huge issues. Interesting. Let's think. Okay, stop messing with indices and think. If the max index is less than list J, so that's right. We go from 0 up to the length of the list minus 1 minus I, which should be okay. Ah. There we go. That fixed it. Okay. Yeah, there's a lot of length of list minus 1 minus I's. I think there's probably better ways to do this, but this is just what I kind of put out very quickly. So anyway, I think this one is a pretty understandable sort. I think, so actually, the sad fact is that this is almost the identical sort, it's just the indices are much more complicated. So anyway, okay. All right, so now let's talk about insertion sort. So insertion sort is a different one. It's almost it's a little bit like selection sort, but it works kind of in the opposite way. What it does is it's kind of like a mixture between bubble sort and selection sort. And what I call it is the pullback sort. So what it does is let's see it run. Okay, that's too fast, way too fast. So here what it's doing is it looks at the element, and what it's going to do is it's going to continuously swap it backwards until it's in the right position. Don't do recursive bubble sort. There are recursive sorts, which we'll get to in just a bit, but don't do recursive bubble or selection or insertion. And so basically, you see why I'm calling this the pullback sort, because what it does is it takes one element and it pulls it back until it's in the right position, and then it stops, right? So unfortunately, the inner loop has to be a while loop, because it has to be while the thing is not in the correct position. And so here it's going to pull it back until like around here, and then it'll stop. This one will pull back all the way until here, right? And then it'll stop. And so you see that they're kind of, it's not, in some cases it's not an improvement, but it does actually reduce the number of swaps from bubble pretty considerably. So experimentally, you might not expect insertion to perform as well as it actually does, but it does actually perform moderately well. It does have to do a huge amount of swapping, though, more than selection sort. So selection sort only does exactly n swaps, where n is the length of the list. Insertion sort's going to do some number of swaps that's more than selection sort, but less than bubble sort. So that's basically the way to think about it. And so you see that basically what happens is the elements are getting pulled back until they're in the right position, and then it will stop. Okay, so that's how insertion sort works, right? So if we look at maybe this one, we can say, let's randomize. Let's do insertion, and then let's run the sort on it. It's hard to say. Selection sort performs better when swapping is inefficient, but insertion sort actually performs the best in terms of all these sorts that we've currently talked about. And you see why I kind of call insertion sort the pullback sort, because what it's doing here is it's actually pulling back the elements all the way until it can insert them. So there we go. This will pull back until it hits 15, and then it'll stop. This will pull, well, actually, no, I'm sorry, that didn't pull back because it was 50. So, okay. So, how do we code this one? All right, what do we do to code insertion sort? And the answer to that is, well, what we're going to have to do is we're going to have to say, for I in range, say 1 to the length of the list. Okay? And then what we have to do here is we have to say, while the list at I minus 1 is bigger than the list at I, and also technically, while I minus 1 is bigger than or equal to 0. And so there's a question of why we need this one. The reason why we need this one is because at the end of the while loop here, I'm going to do an I minus equals 1 here. So as we subtract 1 off of i's, if I minus 1 is equal to -1 or somehow is not in range, then we don't want to actually check this. We want to terminate the loop. So let's think about this then. Okay, so while I is really I is bigger than 1, or bigger than or equal to 1, or technically I is bigger than 0, or something like that. Technically, we can simplify this expression to just I is bigger than 0. Okay, so let's do this then. If we do this, then what we're going to do is we're going to say, okay, now we need to basically, we're going to take the element, so we're going to take is equal to the list at I, and then what we're going to do is we're going to say, okay, the list at I is equal to the list at I minus 1, like this. Oh, cool, so I'll explain that. So here's the thing. When we pull back elements, right, if we look at this thing and we look at a new list, say this, the point is that if you start at the index of 0, you can start at the index of 0, but then you're going to notice one thing. A, there's nothing to swap it back into, and B, a single element is already sorted, so you don't really have to look at this element. Basically, the first thing you should do is you should start at 44, and you look and see if you have to swap it back. Then look at 38 and see if you have to swap it back, and then look at 5 and see if you have to swap it back. So, for instance, here it's going to say 3 is fine, and then let's slow this down just a little bit. Yeah, there we go. So basically here we're going to have to swap this back until here. What was I even saying? I forget. Yeah, so you don't have to swap the first element back because there's nowhere to swap it into. That's basically my point. As I say, if I didn't do this, if I left this off, this would work perfectly fine. This would not cause a problem. It's just that this while loop would not execute, right? Because I is not bigger than 0. So because I need I to be bigger than 0, I just throw the minimum of 1 in there and I save myself, like, I think, one conditional check. Oh, I'm sorry, we actually need to have a temporary, so j is equal to I, while j is bigger than 0. So this is a problem that I made. So why do we need it to be j? Because we cannot, or we should not, change I. Because now we need to be saying that the list at j, let's see, actually, you know what? Instead of doing this, we'll just swap. That solves that problem. And we don't even need this variable now. Perfect. So let's see if this works. Not 100% sure. Let's test it out. Nice. So we see that the insertion sort passed 10 randomized tests. That doesn't necessarily mean it's guaranteed to work, but it probably works if it's passing all those tests. So you see that here, the code for insertion sort is actually, I guess it's the shortest of all the sorts so far. For me, it was always the hardest to understand. I don't know, I always had this was the hardest one for me to understand. And you might ask, but why? And I have no idea. So basically, when I started thinking about it as the pullback sort, and then insert at the, basically all the sorts insert at the correct position. Well, I guess bubble sort of just keeps percolating, but selection sort inserts at the correct position, insert sort kind of inserts at the correct position, but the real thing is that it pulls an element back until the sublist from 0 to I is sorted. Then it indexes up to I plus 1 and repeats, right? So then it sorts then it basically pulls the element at I plus 1 until it's in the sorted position, and then from 0 to I plus 1 is sorted, go to I plus 2, you do the same thing, pull the element back until it's in the right position, and then that thing from 0 to I plus 2 is sorted, I plus 3, do the same thing over and over until you're happy, right? So actually this one is this one's not so bad. Okay. So I think at this point we don't have time to do both. So maybe I will just do one of the two sorts. So next time, you know, we will do, so let me do quick sort this time, and we'll save merge sort, which is my favorite, until last. Okay? So quick sort, by its name, you might think, well, it should be quick, right? But how does quick sort work? So let me talk about how quick sort works. Are log sorts superior? Yes, they are. So now let's talk about quick sort. So this is a logarithmic sort. And what I mean by logarithmic sort is that it technically runs in n log n time, which you probably don't understand yet because we haven't done algorithmic complexity yet, but who cares? The real important fact is that it's going to be faster, and I'll prove it to you by the end of today. So you might not understand or believe me yet, but just the other ones are called quadratic, and I'll explain that too, because in general they take, for a list of size n, the amount of time that they take is proportional to n squared. And for a log sort, the amount of time that the log sort takes is proportional to n times the logarithm of n, which I'll go over once I finish talking about quick sort, about why it's faster. And then we'll actually do some sort races and see which ones are actually faster. So here's the thing. What am I doing? Oh, right, I'm telling you what quick sort is. So here's quick sort in a nutshell. Basically, if you have a list, or let's say if you have an element, a list and an element. So let's say we have a list, say, let's just say we take this unsorted thing here, and then let's make up a new element, let's say 4, okay, is our element, and here is our list. And now, here's the good news. Either things are less than 4, equal to 4, or greater than 4, okay? And so if that's the case, then we should make 3 little extra new lists. So what we're going to do is we're going to make 3 new lists. One of the list is going to be the less list. So we go through this thing and we say, what elements are less? So we say 2 is less, 3 is less, 1 is less. Right? 5 is bigger, 7 is bigger, 9 is bigger. In the equal list, so this is the less list, we got this. And then on the equal list, we're going to stick the element itself and any copies of it. There's no extra copies, so we're only going to make one of them. No extra copies. So only one. And then finally, for the greater list, what we're going to do is we're going to say, okay, 7, 9, and 5. Okay. So now what we're going to do is we are going to, so now that you see that we have it divided into 3 different lists, so the equal list is all going to be made up of 4s, so it's already sorted. This is still unsorted, and this one is still unsorted. And so what are we going to do? I have an idea. Why don't we quick sort the less list, and we'll quick sort the greater list, and then we'll add them all back together. And then we will return this. So now you see, uh-oh, what is this? This is recursion. This is a no bull crap actual factual application of recursion. So you can use recursion. This is a true industry standard recursion, right? So this is recursion. So let's do it. So now what I'm going to do, and you might say, well, okay, but how did you pick this element? The secret is that what you're going to do is you're going to take this list and you're going to pick 2 as the element. Just make the first element the pivot. And that's what we call it. It's a term of art. And what I mean by term of art is it's a made-up word that means nothing, but we just call it the pivot. And so now we're going to make a less list. The less list is 1, equal list is 2, greater list is 3. And at this point, this thing is sorted because we can do 1 plus 2 plus 3, which will be 1, 2, 3. It's sorted. We can return it. So now we do the same thing with the greater list. Okay? We do the same thing with the greater list. We pick 7. And you might think, well, what if there's a better choice than 7? Who cares? Yeah, it might hint to you something about Gauss-Jordan reduction or something like that. Do not think about that too hard. The analogy will break your brain. So 5 is the less list, 7 is the equal list, and 9 is the greater list. So the element should always be the first thing. Yeah. In a perfect world, and I'll go over all of this probably next time, you would not necessarily pick the first element as your pivot. But in the ultra basic version of quicksort, which is what we're doing the mega ultra uber basic version of quicksort with no optimizations. You pick the first element as the pivot. Okay, so now the point is here, you have 5, 7, 9, so basically 5, 7, 9, and now it's sorted. So basically then what happens is this gets returned, and we were in this statement here, right? So this statement becomes return, what does it become? Return 1, 2, 3, plus 4, plus 5, 7, 9. And so that will return the complete sorted list. And you're like, huh, well that kind of worked, right? What you do is you take an element, you break it into 3 parts, the things that are less, the things that are greater, and the things that are equal. And then you sort the less stuff, you sort the greater stuff, and you keep the equal stuff because you don't need to sort it. And then, what do you do after that? You're done, right? Because the recursion takes care of the rest. If the smaller list needs to then be broken up again or again or again, that happens, right? Because this is recursion. So if you have a long enough list that it needs to be broken up, say 4 or 5 times, then it'll do that. How does quicksort know when to stop? And that's a good question. So that is, your question is equivalent to what is the base case, base case for the recursion in quicksort? And the answer is, yeah, no, exactly. So I'm literally just rephrasing your question. Your question was perfectly well stated. The thing that, what is the base case? The base case is if you have a list of size, say 1 or 0, right? Because if I pass you a list and say 17, is that sorted? You'll say, I guess, sure, right? And if I pass you an empty list and I say, is that sorted? You'll be like, oh god, I have no apples in a basket. Are the apples in order? And the answer is yes. Don't think too hard. Right? So basically, if the list has 0 or 1 elements, then the thing is already considered sorted. So we don't have to do any additional work. And so that's our base case. So if the list is size of greater than 1, then we have to do some of this division and stuff. If the list is of size 2, you can always, don't even worry about it. Let's just write the code, okay? Or maybe let's do a visualization of it first. Let's do a quicksort visualization, and let's see what happens. So I guess 3 is going to be the pivot. And so you see what's happening here. Everything is less until there. There we go. So this is kind of an in-place quicksort. What it's doing is it's, let me explain what it's actually doing here. Pause. Okay, I did pause and it's still playing. Okay, it won't stop. The good news is that, actually there's no good news. I actually really did want to pause. Okay, let's try it again. Quick sort, create a list, go, sort. Let's make a new random list. Let's pick one with a better initial pivot. I want something with a pivot that, I guess that one was closer. Stop giving me crappy lists. Here's something that's okay. So the reason why I say that this is okay is because if you notice, what it's going to do is this version of quicksort does some swapping. What it's going to do is it's going to swap all the things that are in the quote-unquote less list. It's going to push them ahead towards the front of the list, and it's going to put everything that's in the greater list towards the end. So let's just watch it as it does this. And so there we go. So now we have the pivot element, the less list, and the greater list, right? And so now it's going to swap this one into this position, and then it's going to sort the less list. So let's watch that happen. Right, so now it's doing a recursive quicksort. There we go. The pivot is that, swap, okay. And then here, well, that's confusing, but the point is that with all these swaps, it gets a little confusing, but you don't actually need to have it swap. We're doing an out-of-place quicksort. So there's an in-place quicksort, which is this. There's the out-of-place quicksort, which is what we're doing. So let's see what quicksort does in this visualization, and hopefully it doesn't just explode. Okay. It's kind of doing the same thing. You notice that it's putting everything that is in the less list at the front. You can definitely sort strings. You can sort anything that's quote-unquote comparable. And what I mean by comparable is if it has a less than and an equal to sign. So if you have a less than sign that works and an equal to sign that works, then you can do it. So you can sort strings, you can sort numbers, you can sort other things that can be converted into strings or numbers. And so, yeah, so that's basically how that works. You can sort a lot of things. Generally, we only talk about sorting numbers because it's the easiest way to do it, but if you call sort on a list of strings, it'll put them in ASCII alphabetical order. Okay, so that's how quicksort works. Quicksort divides the list, so let's make a quicksort function. All right, the list. So if the length of the list is, say, in 0 or 1, then we can just return the list, right? This is our base case. But what if it's not? So now let's make our lists. So less list equals empty list. Greater list equals empty list. Equal list equals empty list. And now what I'm going to do is I'm going to go through our current list. And I'm going to say, and let me name the pivot. So you don't actually have to do this because it's just making a new variable, but I'm going to do it just so that you know which thing is the pivot. There we go. LFX is equal to the pivot. We'll put it in the equal list. Append x. LFX is bigger than the pivot. You put it in the greater list. And there we go, we're done, almost. So now what we have to do is exactly what I showed you before, is we return the quicksort on the less list plus the equal list plus the quicksort on the greater list. All right, and that's it. That's quicksort. So basically, you just pick an element, you put everything that's less than it in one list, you put everything that's equal to it in another list, and there's a reason why I do this. It's not 100% standard in the quicksort algorithm, so you might see some quicksorts without an equal list. Sometimes they do it just with a less or a greater list, and they just stick all the equal elements into the greater list. There's a reason that I do this, mainly to it prevents some annoyances. So anyway, so the greater list append x, and then we quicksort the less list, we quicksort the greater list, and then we're happy, right? So now let's run our test on quicksort and see if I coded quicksort correctly. Ooh, totally wrong. Everything is bad. What have I done? Oh, I think maybe the test is... Let's see. Let's see if this fixed it. Yep, okay. Actually, the testing function had a bug in it. Okay, so the... Yeah. Oh well, okay, cool. So I think quicksort's basically working. So now I don't want to spend too much... Well, I guess we have about 5 minutes left in class. And so basically what I'm going to do in these 5 minutes is I'm going to copy a little time testing function that I had from a previous semester. Let's see. I think... where did I have it? Is it here? Let's see what I did. Ah, indeed it would. Yes, that is correct. Okay, where is the sort time test function? Okay. All right, and let us not actually test it on anything. Let's first test it on, let's modify this for just a second. Let's say size 10, size 100, size 1,000. So okay. All right, so let's see what happens here. So let's not do a sort test, let's do a time test on, say, bubble sort. Okay. You do, except that it's forbidden because you can't import it, right, in most of your stuff. So you have to import it, which is generally forbidden, but if I ever need you to do it, then you can do it. The point is that you're not going to need it until you get out of this class anyway, but yes, I mean, technically, you can use it if I allow it. So let's do a time test on bubble sort and see how long it takes to sort 10, 100, and 1,000 things. Let's run it on 3 tests each. So here we go. Whoa. Okay, that's gonna be bad. Let's get rid of this print statement. Let me make sure I get rid of the print. Is there a print statement in selection sort? There is. Let's get rid of that too. Okay. So here it doesn't detect the time, mainly because it's smaller than the... This time function doesn't detect things that are smaller than about a millisecond. So here it just didn't quite detect it. You notice that the time is going between about 1 millisecond, 1.5 milliseconds, and 2 milliseconds. So that's what that is. And so you notice here, so this is why we would call bubble sort a quadratic sort, okay? And let us add a 10,000 in here. So we notice, if we pull up ye olde Windows calculator, that if we take 0.001 seconds and multiply it by approximately 100, we get about 0.1 second. And this is about 0.16 seconds, and you're like, well, that's close enough. And then here we're multiplying the size again by 10, but it's an n squared sort, so that basically if you multiply the size by 10, you actually have to multiply the time by 100. So you notice here that it took 0.16 seconds to sort something of size 1,000, but it's taking about 16 seconds, right? Crap. 1,000 times 0.16 is 16 seconds approximately. And so you see here that bubble sort, every time you increase the size of the list by about a factor of 10, you're going to increase the amount of time by about a factor of 100. And that's why we call it a quadratic sort, because 10 squared is 100. Okay. Well, now, just to round out the class before we do some other stuff, let's run it on, say, insertion sort. Okay? And then finally we'll run it on, there we go. Okay, let's try this. So you see that insertion sort did a little bit better, right? Instead of being 0.16, it was more uniformly 0.10 seconds on the same size. And here it should take about 10 seconds, right? So you see here, insertion sort is performing better than bubble sort, but it's not performing asymptotically better, meaning that bubble sort took 0.16 seconds on 1,000 elements, and it took 16 seconds on 10,000 elements. Here, this took about 11 seconds, or 0.11 seconds on 1,000 elements, and it takes somewhere like 10.5 seconds on 10,000 elements, which is still 100 times worse, right? That's still 100 times worse. And so it's not performing, it is performing faster than bubble sort, right? It is faster than bubble sort, no argument. But it's not asymptotically faster because it's not actually increasing, it's not, I shouldn't say increasing, it's not decreasing the overall factor by which the time increases. Okay, so let's do quicksort now and see what it makes of this. Boom. All right, so quicksort is pretty quick, as you notice. So unlike taking 0.1 seconds on a size 1,000 list, it actually only takes 0.001 seconds to sort a size 1,000 list. And then you also notice here, that here's the cool part, you increased the size of the list by, or I increased the size of the list by about 10, and you notice that the factor, right, that it actually increased the size of the runtime was only by about a factor of about 10. So it's actually n log n, but the good news is that the log n part kind of disappears a little bit with quicksort. Quicksort actually performs a little bit better than its like average case runtime sometimes, and this is an example of why. So if you notice this, then basically, if the 0.001 seconds was a quadratic sort, then you know that this sort would take 0.1 seconds. But it's actually not taking that, it's 0.01 seconds. So it's actually, this is 10 times better, right, than the corresponding quadratic sorts. It's also a huge amount faster, right, because this took 16 seconds, and this took 0.01 seconds. So it's still, what, you know, 1,600 times faster, something like that, than bubble sort, and about 1,100 times faster than insertion sort. So yeah. So basically that's the point. That's the moral here, right? And you could even increase the size that we were going to sort on and go up to even say 1,000,000, right? And by 1,000,000 you're going to start noticing the time. But see, even at 100,000, we're getting about 0.1 seconds. Are there any benefits to using quadratic sorts over logarithmic sorts? The answer is no, not really. The only thing about okay, I shouldn't say that. The answer is yes, and I will explain that next time. Well, so you could sort strings, right? Because it has a less than sign. So it works. So you can sort strings. I just basically we're just sorting numbers because numbers are usually the easiest things to sort. If you want to sort strings, you can do that. Though sometimes, anyway, the runtime depends on the length of the average string as well as the number of elements in the list and stuff like that. But anyway, I think that's all for today. We haven't done my favorite sort. So next time what I'm gonna do is I'm gonna go over these sorts again. I'll play the visualizations again. We'll go through some of this, and then what we'll do is we will code up my favorite sort, which is merge sort. So we haven't coded merge. Merge might not be as good as, sadly, not heap sort, because I generally have to tell them what a heap is, and I don't want to do that. So, yeah, no heap sort, no radix sort. Yeah, merge sort is my favorite. I don't know why. It's completely arbitrary. I don't have a good reason for it. I just like merge sort. Anyway, okay, so that's everything I have for today because we have done 4 different sorts, and that's pretty good. Okay, so next time we'll do the 5th sort, and then we'll kind of talk more about time complexity, and we'll talk about what all these numbers mean, and we'll do some more time tests and sort racing and stuff like that. Yeah. Okay. That's really it. And I'll post this to the GitHub so you can see all the different sorting algorithms. You can run your own sort races. It's unfair, of course. The quadratic sorts are at a huge disadvantage and they really can't win, but, you know, life isn't always fair. Sometimes a quadratic sort just can't win. All right, and with that, I'll let you go. It's uploaded to the GitHub. You can go and play with it if you want. And all right, I'll let you go.